In this screencast, we are going to talk about reactions of epoxides. Now, although epoxides do not contain a good leaving group, they do contain this strained three-membered ring with two polar bonds. So what we find is that nucleophilic attack will open up the strained three-member ring, making it a favorable process even with this poor leaving group. Now, nucleophilic addition to epoxides occurs readily with strong nucleophiles and with acids like HZ, where Z is a nucleophilic atom. So let's just make a note of that. Nucleophilic addition to epoxides occur readily with strong nucleophiles and with acids like HZ, where Z is a nucleophilic atom. Okay, and there are two examples here. So we identify strong nucleophiles because they have this negative charge on them, right? And then this would be like HZ, where this is also a nucleophile. And you can see how in this reaction, right, the nucleophile has attacked one of the carbons of the epoxide ring, right? And when we talk about this kind of carbon, it's important to remember that it is electron deficient. So it's going to have a partial positive charge there. And this is, we're going to talk about what we do when it's not symmetrical, but this is symmetrical right now. It's the same on both sides. So it doesn't matter which side the nucleophile attacks. So the nucleophile is going to come up here. It's going to attack the partially positive carbon. And this is an SN2 mechanism, right? And it causes the electrons here to come up onto the oxygen, and that cleaves the carbon-oxygen bond here. And that relieves the strain on the three-membered ring. And so the nucleophile now is attached to one of the carbons, and then there's an oxygen here. Now, in the second step here, the alkoxide is protonated with water to generate a neutral atom here. And this is just a generic proton transfer, right, like that. That's it. That's all that's going on. So common nucleophiles that you see here are things like OH minus, OR minus, CN minus, thiol SR minus, right, and NH3. Now, NH3 does not have a negative attached to it, but remember, it's got that lone pair on the nitrogen, okay? So let's talk about stereochemistry for just a minute. This reaction occurs via an SN2 mechanism, and that results in kind of two things. When we look at this reaction, okay, and we have these electrons coming in here to attack that partially positive carbon, and those electrons go up onto the oxygen. That is a backside attack. So that's an SN2 backside attack. And when this happens, we see the oxygen that's deprotonated is right here, okay? And then we have the hydrogens here, and here, and here, and now we have that O CH3 group bonded there. Then when we add the water to protonate the alcohol, we get this product. And the big thing here is that the CH3, let's say the OCH3 and the OH are anti in the product, right? Where we see up here, one is up and then the other is down. So they're on opposite sides. They're around that single bond. Now, in an unsymmetrical epoxide, the nucleophile attacks the less substituted carbon. So let's look at that. So for example, if we have this epoxide, and we have this friendly nucleophile coming in to attack it, what we're going to find is that it is going to attack at the less substituted carbon. That means that's the carbon with fewer substituents attached to it. So this has 2 substituents, this does not. This is going to have hydrogens instead. And so that opens the ring like that. Right, and then we react it with water for a proton transfer. Okay, let's look at kind of another situation that we can run into with stereochemistry. When we look at this example of 1,2-epoxy cyclohexane undergoing the nucleophilic substitution reaction, what we find is that we have an achiral starting material and we end up with an equal mixture of enantiomers here. So what happens is that nucleophilic attack occurs from the backside at either bond shown here. So it can come in above the plane or below the plane, because both ends are similarly substituted. Now, since the attack at either side occurs with equal probability, an equal amount of the 2 enantiomers here is formed, and that's a racemic mixture. And so what we find here, and we can make an overall generalization as well, is that optically inactive starting materials like this is an achiral starting material, give optically inactive products. Now this is optically inactive because you have equal amounts of A and B, and those of course rotate in different directions in plane polarized light. So that concludes our discussion of ring opening reactions with strong nucleophiles in epoxides. And so now we are going to transition to talk about acidic epoxide ring openings. So acids that contain the nucleophile Z are also open epoxide rings by a 2-step sequence. So acids HZ, where Z is the nucleophile, also open epoxide rings. By a 2-step sequence. Right? And so let's look at that. All right. So in the first step here, there's protonation of the epoxide oxygen, right, through a proton transfer reaction, where those electrons are going to go out and grab that proton, and those electrons go back on that nucleophile. Now, after that occurs, right, now that oxygen is protonated, so it's got a positive charge. Right? And the nucleophile then comes back in and attacks either this carbon or this carbon. Now, in this example, it does not matter which carbon it is because they are both equally substituted, right? They're symmetric. So what we're going to see here for this example is I'm going to have it come in and attack that carbon. When it attacks that carbon, those electrons go back onto the oxygen and we end up with an alcohol bond. And so okay, and it looks like that. Now, what type of acids tend to open these rings? Well, when we look at this, what we'll find is that acids like HCl, HBr, HI, as well as H2O and ROH, right, as long as you add an acid, right? So, for example, this would be one of those halogen acids being added, HBr, right? But this would be an example where you had water and then a little bit of an acid added as well for that ring opening reaction. Now, the ring opening of an epoxide with either that strong nucleophile or an acid, HZ, is regioselective because one constitutional isomer is the major or exclusive product. And so the site selectivity of these two reactions, though, is exactly the opposite. And so what do we mean by that? Well, let's look at these two examples here. So I have an example for you where we're going to use the exact same epoxide. So we've got this epoxide here, and then this epoxide here, okay? And we're going to come here and we're going to say, look, we've got OCH3 minus and water, and then we have CH3OH and H2SO4, okay? So, with a strong nucleophile, attack occurs at the less substituted carbon. This has a negative charge. It's a strong nucleophile. So that means it's going to attack at this less substituted carbon. So that means it's going to come in here and attack here. And then those electrons are going to go on that oxygen. And then the H2O is going to protonate it. And so what you're going to end up with is this molecule, and then of course we have H2O, and then that protonates it, and then we end up with that molecule there. Now, with an acid like HZ, the nucleophile attacks the more substituted carbon. Now, I want to show you something. This is exactly what your book says. But look, this is a weak nucleophile with an acid, and so it falls under, right, this umbrella here. So it's going to attack at the more substituted carbon, which is this carbon here. And so what we're going to form then is that molecule there. And so these are two examples where we have a strong nucleophile and we have an acid with a weak nucleophile, and we can see how it attacks in different places. Now, let's talk about the mechanism of this for just a moment, and we're going to look at an acid HZ, because if you have an acid HZ, it follows this rule too, right? When we come over here and we look at this, right? This mechanism is somewhere between an SN1 and an SN2. So the first thing that happens is that group is protonated, right? And so we have this group here. Now we have, when this comes up to attack this molecule here, we have two different transition states, okay? You can have a transition state where there's a partial positive on the less substituted here, or a transition state where the partial positive is on the more substituted here. Remember that these alkyl groups donate electron density to stabilize a partial positive charge. So because of this, that stabilization, that is why the chlorine is added to the carbon with more substituents. And so this product is formed. Now, the reason we say this is somewhere between an SN1 and an SN2 is nucleophilic attack occurs from the back side, which is an SN2 characteristic, at the more substituted carbon, which is an SN1 characteristic. So that's why it has characteristics of both, okay? All right, this ends our discussion of epoxide reactions. If you have any questions, please feel free to reach out. This also ends our discussion of Chapter 9. Again, if you have questions, please feel free to stop by my office. I am happy to help.